We're going to take a look at 8.5 Part 2. In this section, we're mostly going to focus on doing operations with vectors without sketching them. The only sketches that we'll probably do is if it relates to a word problem. All right, so let's suppose that we had two different vectors. Let's say one of them looks like this, and the other one looked like that. Do you think those two vectors are equal? Exactly the way just drawn just like that. Anyone have a thought? Equal or not equal, those two vectors? Well, Colin, what do you think?
They look equal.
They look equal?
Yeah.
Even though they're not in the same spot? Do you think they're equal vectors?
I guess they're not equal then.
You let me change your mind. Yeah?
They would be similar but not equal, at least as far as I can tell without the difference telling me exactly.
Okay, so yeah, there definitely seems to be a little confusion. Are they equal or are they not equal? They are copies of each other. So does that make them equal though if they're in different spots? Yes, it does. Okay. For two vectors to be equal, their components have to be equal. So the way you would figure out the components is if you made a triangle out of each of them, like that, and if you drew in the horizontal component of that vector, it would look like that. The horizontal component of that one looks like that. If those two red arrows match, then that means these are the same. Now, you draw in your vertical component here, draw in your vertical here, and if those two blue arrows are exactly the same length, then those would match. If the x's match and the y's match, then they are equal to each other. So for vectors to be equal, it does not mean they are in the same spot. It means the components have the same length. Right? And the components have to also be pointing in the same direction, because I could draw a vector that has these components flipped. So like this vector going down and to the left. In that case, the components would be the same length, but they wouldn't have the same direction. Okay? So the two vectors to be equal, the components each point the same way, and they're each exactly the same length. Even if they're in different spots, that's fine. Okay? Any question on that idea? All right. So the next concept we're going to look at has to do with another way that we can write vectors, but not using that algebraic notation. Okay, it's called unit vector notation. When I talked about naming vectors yesterday, I said there's three letters you don't want to use because they're something else. Does anybody remember what the three letters were for vectors? Yeah?
I, J, K.
Yeah, I, J, and K. We're not going to talk about K right now because that's for 3D. Okay, we're going to talk about I and J. So I, when you are referring to vectors, is a special name. And I is what we call a unit vector that points one unit to the right. Remind me again, what does it mean if it's a unit vector? It means something special. Yeah. The magnitude is 1. Yep. So I is a unit vector that points to the right. That is what I looks like. It's 1 unit long and it points right. Now when we're dealing with 2D, I can say up, down, left, and right and it makes sense. When we get to 3D, I can't really use those words, okay, because we're going to have x-axis, y-axis, and z-axis. So if I was describing this vector in 3D, I would say it's 1 unit long and it points in the direction of the positive x-axis. However you want to think of that axis in 3D. Okay, with j, that's another special unit vector. And if I was describing it on a 3D coordinate system, I would say it's 1 unit long, and it points in the direction of the positive y-axis, whichever way the y-axis is in 3D. When we're dealing with 2D, I can use the direction up. Okay, so it's a little simpler in 2D. So j is a unit vector, points up, and it looks just like that. That's j. Okay, so I, j. And the idea of unit vectors is you kind of think of them as building blocks. We're going to stack them together to make a vector. So what we're going to look at now is how do we convert something from the algebraic notation like this into what we call unit vector notation. All right, so let's take a look at the vector 3, 4. Okay, from yesterday, what doesn't this notation tell me? I want to make a sketch of that. If there is something it doesn't tell me, it doesn't really matter, but I just want to make sure we remember. Yep. Yeah, it doesn't tell me where to start, so I'm going to start right there. I can start anywhere. I just want to make sure I stay on the grid. So the vector 3, 4 means I'm going to go 3 to the right, 4 up, and there's a picture of the vector 3, 4. Now I want to see if I can build that vector with i's and j's. Let's start with I. That's I. How many i's would I have to stack together? Again, that's just the horizontal movement to start getting from this point up to that point. Yeah?
To the right?
Yeah.
We have to go. Sorry. Yeah, 3 over.
Yeah, we're going to have to stack 3 of them. So I could make 3 copies of it, or it's 1 unit long. I can just draw it by hand. Right? I would stack 1, 2, 3 of them together. If I draw that vector now, like that, what is the vector that I just drew right there? How would you name it? Yep.
3i.
It's 3i. Yep. Now, we still have more we're going to add on to the end of it. That's the start. You need 3 i's plus how many of the j vectors do we need to add on the end of this to get up to the terminal point? Yep.
4.
4. 1, 2, 3, 4. What is this vector on the side? Yep.
4j.
4j. So if you take, let's see if I drew it right. If you take, I didn't get my arrow. If you take the vector 3i, which has an arrow on the end of it, and you take the vector 4j, which also has an arrow. Let's move that down a little bit. And you put 4j on the end of 3i, and then you connect them the way we learned yesterday, from the beginning to the end, you just built the vector 3, 4. So in unit vector notation, this is the vector 3i plus 4j. And we'll practice writing a lot of vectors that way today. Now, if you only use i's and j's, well, I points to the right, j points up. But what if I wanted to build a vector like that? What would I have to do to build that out of i's and j's? Yeah?
You do negative I?
Yeah, we can do negative I or we can do negative j. So between having positives and negative i's and j's, we can move up, down, left, and right. We can travel any direction that we want to build a vector. Okay. And if you had to build a vector like this, something like that, that doesn't land right on an intersection point of the axes. You can use a half eye, or you can use a third eye. You can use any fractional amount of i's and j's as well. Okay. So that allows you to build any vector that you would want in 2D. Not 3D, but it does work for 2D. When we get to 3D, we'll have k, which is a vector that comes out, like out of the board or into the board, if you want to think positive and negative. All right, so now we're going to look at some formulas for vectors. These are 3 out of 4 of the things I'm going to put on the board we've already done. Add, subtract, and scale. But this time we're going to learn how to do them without sketching. Okay, so the 2 vectors I'm going to use in my example are v and w. Each vector has its own horizontal and vertical components. And if I use alpha anywhere in the formulas, alpha is a scalar. Can someone remind me, when you scale a vector, what are the different things that can happen? Yeah.
The magnitude can change.
Okay, magnitude can change, and we can break that down and be a little more specific. 2 cases, yeah.
It can get shorter.
Shorter, yep.
It can get longer.
Longer. So that's it for magnitude, and there's one other thing that can happen. Yep.
The direction can change.
The direction can change if your scalar was a what? Negative. Yep. All right, so let's look at how we're going to add 2 vectors together. Okay, old way. Take a vector, put another vector on the end of it, and then connect where you started to the finish. New way, all we have to do is combine the components. Take your horizontal components from each vector, add them up, comma, and take your vertical components from each vector and add them up. Right, now subtraction. If we wanted to subtract 2 vectors, you'd have to take the first vector, flip the second vector around, put it on the end of the first, and then draw in your diagonal. Well, now, doing it numerically, it's going to be a lot faster. Just take the horizontal components, subtract them, take the vertical components, and subtract them. When we're doing subtraction, is the order important? Yeah. So when you are subtracting, you need to make sure you take the components from V and subtract the components from them. Okay, the next one is going to be a scalar. Okay, this is a scalar product. If I took this vector, let's say I tripled it. Anybody have a guess what the new vector would be? If you took this vector and times it by 3. Yep.
6, 18.
Yeah, you think it's kind of like a distributive property. You multiply each component by the scalar. So horizontal gets multiplied by the scalar, and then the vertical gets multiplied by the scalar. All of these formulas can be extended to 3D very easily. With adding and subtracting, you've got one more calculation on the end for the z values. I guess for now, you could kind of think of the z values as being zeros. We don't have them yet. And the last one. What does that symbol mean? Yeah?
There's a magnitude.
Magnitude, yep. And when we draw a vector and we want to find the magnitude of it, I actually have a good picture of it right there. Anybody have an idea what theorem we're going to use? Yeah?
Pythagorean theorem.
Yeah. To find the magnitude of a vector, you turn it into a right triangle and then do the horizontal component squared, the vertical component squared, add them up and take the square root. So it's a Pythagorean deal. Horizontal squared, vertical squared, add them up, take the square root. Same rules apply to those square roots that always apply. You can't leave any square roots in the bottom of a fraction if anything like that comes up. You also want to simplify square roots as much as you can. All right, any questions on those 4 formulas? All right, let's try one of each one. So I'm giving you 2 vectors. I'm giving them in unit vector notation and algebraic. And we'll write our answer both ways. Let's start with v plus w. All right. So when you're combining them, think of just like combining like terms. You can combine the horizontals together and the verticals together and keep them separate when you're done. Anyone think they can tell me what v plus w would be in unit vector notation? Yeah.
5i minus 1j.
Yeah. So you can do 5i minus 1j, or you can just do minus j. That's fine. And then if we write it with the angle bracket notation, what would be my numbers inside the brackets? Yeah?
5, -1.
Right. This time, you do have to put the -1, because if you don't, there's nothing there. That's it. That's adding the 2 vectors together. So that takes the place of stacking them up and then drawing it in. All right. Let's try v minus w. Okay. Anyone think they can tell me what v minus w would be in unit vector notation? Yeah, Charles?
-I plus 7j.
Yeah. And how about in the other format?
-1, comma 7.
-1, comma 7. Yep. You're not going to have to write both notations on the test. It's going to be one or the other. Okay. But you might see both notations throughout the entire test. Okay. All right. How about 3v? What's going to be 3v in unit vector notation? Yeah, Colin.
6i plus 9j.
Yes, 6i plus 9j. Or the other way you could do it is
6, comma 9
like that.
in the bracket.
In the brackets, yes. Okay, any question on that one? All right, and this one. Magnitude of v. Okay, what's going to be the calculation or expression that I set up to find the magnitude of v? Yeah.
The square root of x1 squared plus y1 squared.
Okay. And for v, what would you fill in for those 2 variables?
You would fill in 2 squared plus 3 squared.
2 squared plus 3 squared. And we're just going to leave this as an exact answer. And what would that give me?
$13.
13. Okay, is that unit vector form or is that algebraic form? Yeah?
Algebraic? Maybe? I don't know.
Square.
It's not algebraic. Yep,
Unit vector. Or I guess neither of them.
neither. That's not a vector. When you're finding a magnitude, the answer is a number. When you add vectors, you get a vector. When you subtract vectors, you get a vector. When you scale, you get a vector. When you find magnitude, you get a number. Okay, so that is not a vector at all. It's the square root of 13, and you can type it in as a decimal if they ask for it. Any questions on add, subtract, scale, and magnitude without any sketches? Okay. So just see if you can remind me, kind of just said it, but if a vector has a length of 1, we call it what? Unit vector. So what we want to look at now is how do we find a unit vector if we are given a vector that is not a unit vector? Well, look at the black vector and the red vector. Out of the first 3 things we just did on the last page, adding vectors, subtracting vectors, and scaling vectors, which one of those operations would turn the black one into the red one? Add, subtract, or scale? Yeah?
Scale.
Scale. So if you're given a vector and it's not a unit vector, you need to scale it. That's how you make it a unit vector. Does anybody know in general what you could always scale a vector by and its length would turn into 1 unit? Yeah?
Itself?
So if it was 5 units long, scale it by 5?
Yeah.
Well, that would make it 25. If it was 5 units long and you scaled it by 5. Yeah?
It's fractionally reciprocal.
Yeah, it's reciprocal. Yep. So I did a few examples in the last class. We did the length and then the scale factor. If something is 5 units long, you would scale it by 1/5, and that would make it 1 unit. If something was 8 units long, what would you scale it by? Yep.
1/8.
1/8. If something was a half a unit long, what would you scale it by to make it 1 unit? Yep. 2. Yeah, it's always the reciprocal. Right? The reciprocal of the magnitude. So what we're doing is we're finding a new vector, okay, like the red and the black one. The red one is the new one. The red one points in the same direction, but it's only 1 unit long instead of however many units it was. So you scale the vector by the reciprocal of the magnitude. So if you had vector v, and you want to convert that into a unit vector, you're going to find the magnitude, you're going to flip it, and you're going to multiply by that number times your vector. Now, you can also put that all together. If you want to put the v in the top, that's fine, because you can just multiply 1 times v. V in the top, magnitude of v in the bottom. Okay, and that will always turn a vector into a unit vector. There's only one vector you can't turn into the unit vector. What vector is that?
0 vector.
Right, the 0 vector, because it has a magnitude of 0, and if you flip 0, you get undefined. So you can't use the reciprocal of the magnitude. But that's a special case. So let's find the unit vector for 3i minus 4j. Okay, and I'm giving you both notations again. I wouldn't expect to always see both, probably one or the other. All right, so what's the first thing that we need to find if we want to turn that into a unit vector? Yeah. Find its magnitude. If it already is 1, well, you're done. There's nothing to do. If it's not 1, then we fix it. someone else give me the formula to find the magnitude of V? Not all at once, though. I don't want to get overwhelmed or anything. Yeah. Wait.
It would be, square root of -4 squared. Of 3 squared plus -4 squared.
So 3 squared plus -4 squared. The order technically doesn't matter because it's commutative when you add, and the negative is going to cancel when you square it anyway. What's that going to give me a magnitude of for this vector? Yeah, Ashley.
5.
That gives me 5. Yep. So this vector, is it a unit vector or not a unit vector? You think? Yeah.
It's not.
It's not. What do we have to scale it by to make it a unit vector?
1/5.
We have to make it 5 times shorter. So take your original vector and find 1/5 of it. If I write vector v scaled by 1/5, what's going to be my answer in unit vector notation? You can leave fractions in the answer, that's okay too. Yeah. yeah. 3/5 I minus, what was it? 4/5 j. Yep. That's the unit vector. It's been scaled to be 5 times shorter. So if it was 5 units, and it's 5 times as short, now it's 1 unit. And that's what we're looking for. Yeah. Any question on how we scaled that to turn it into a unit vector? Yes?
Is that exactly how you want it written on the test, or do you want like what the decimal would be?
I would say for that one, I would just leave it as a fraction. Yeah. Especially, if you get one like 3/7 as a fraction, that's not a nice number. So if we can avoid rounding, it's better to avoid. Okay. Any other questions on that one? Okay. So, the last 2 things we're going to look at are both applications of vectors. First one's a little bit easier, second one is a little bit more to it. Okay, but one thing we talked about that you can use vectors for is velocity, okay, speeds. What was the other example I gave yesterday that you could use vectors for? Yeah? Force, that's going to be the second one. Can somebody give me, and it can be any example you want, but just give me any vector that's a unit vector notation. Can someone just give me any vector? Yep.
3i plus 4j.
3i plus 4j. What do we call this part of the vector? It's the, yep. It's not a coordinate, so it's not an initial point. Like I know in the homework they gave you an initial and a terminal point. But that's a vector. Yep.
The horizontal component?
That's the horizontal component of the vector if you break it into a triangle. And what about this number? Yep. That's the vertical component. So when you write a velocity vector, first of all, it has to be a vector. You need to break the velocity into its components. So what does that mean? Well, if you have an object that's being thrown, it's going to be thrown at a certain angle. The angle you throw the object at is relative to the ground. Okay? 90 degrees would be straight up. 0 degrees would be perfectly parallel to the ground. Couple things we're going to assume. Normally, when you throw an object, the curve of it, or the path of it would be a curve, because it would come back down. We'll assume maybe we're doing it in like outer space. It just keeps going in a straight line. So it's not affected by gravity. All right. So what would I have to do in that diagram to visually show how I'm going to break that vector into its components? We don't have to do any like arithmetic yet or trig. We just want to figure out like a picture that would show somebody the components of that vector. Yeah?
Make it a right triangle.
Right, we're going to make it into a right triangle. So now we have two vectors. What is the direction that, if you want to describe it as up, down, left, and right, what is the direction that that vector is pointing in right now? Yeah.
Up and to the right.
Up and to the right. So that vector is a combination of two. It's a combination of a vector that goes up, and it's a combination of a vector that goes to the right. Let's call this the length of the bottom one x, and we'll call the length of the green one y. What would be a trig function that relates this angle, the side that's x, and the vector v? Yep,
Cosine?
cosine. And when we write cosine, it's a fraction. What's the fraction that goes on the other side for cosine? It's 1 over 1. Yeah. So it's the what goes in the top? No, not for cosine. That is a valid side, but just not for this trig function. Yeah.
Adjacent over hypotenuse.
And what about the adjacent over the, like the color of the adjacent over the color of the hypotenuse?
The variable. So y over the vector.
Well, what is the, like when you say adjacent over hypotenuse, like what
Oh.
are you saying? Like how heavy the adjacent side is? Over how heavy the length, yeah. It's the length of the adjacent over the length of the hypotenuse. What's the length of the adjacent in that picture? Yeah?
X.
X, right? Because that's how I labeled it. X is a variable that represents length. What is the length of the hypotenuse? Yeah?
Vector.
It's a vector, though. A vector has two parts. Only one part is the length.
Be the magnitude.
The magnitude, yes. So it's the length of the adjacent over the length of the hypotenuse. So we need the magnitude symbol there. So what would that mean that the x is equal to? And x is my horizontal component. Olivia?
The magnitude of cosine theta.
Magnitude of v. We're just going to pretend it's bold. It starts getting messy if I keep putting that arrow up there. Cosine theta. That's the formula for the horizontal component of a velocity vector. And anyone have an idea what the formula for the vertical component would be? Yep.
The magnitude of vector v times sine theta.
Yeah, the magnitude of the vector times the sine of the angle. Anytime you're breaking a vector up into its components and you want to know the horizontal, it's always cosine. If you want to know the vertical component, it's always sine. And it ends up being hypotenuse in the front of it. Hypotenuse cosine, hypotenuse sine. That's horizontal and vertical. All right, so now we can write our velocity vector. A velocity vector, if you want to do it in the notation I taught you yesterday, magnitude v cosine theta, magnitude v sine theta. If you want to do it as a unit vector, you can do that too. Magnitude v cosine theta I, and then magnitude v sine theta j. So two different ways to write a velocity vector. So what does the magnitude of v and the theta represent? Well, when you're doing a word problem, the magnitude of v, that's the length of the vector, that's the speed that the object was thrown at. So the initial speed is your magnitude of v, and theta, that is the angle the object is thrown at. So I'll just say use the previous formula because we just wrote it down. That's the formula right there. All you got to do is fill in the magnitude, which is the speed, and the angle that it was thrown at. You might see different Greek letters used for the angle. You can use any variable you want. Just understand that the angle is what the object with the ground. It's the object, the path of the object. All right. Anybody still need to copy down the formula? So let's say that we have an object being thrown at 50 miles an hour. The angle is 30 degrees. Find the velocity vector in unit vector form. And then once we have each component, I want to explain what the meaning of it is. All right, so let's start with our horizontal. What's going to be the formula for this part of my velocity vector? Oh, Emma, can you tell me what that part would be? So what are the two things we have to fill in on that first part? Like what are my two variables in that first part of that formula? So I'm looking for letters. Two letters we have to fill in for. But one of them is representing length. Yeah. Which one? Yeah, the magnitude of v. So that's like the length of the vector, which is what in this problem? So what is when you draw a velocity vector, what does its length mean? It's the what? The speed, yep. So in this case, what would be the magnitude of V? 50, yep. So you're gonna fill in 50 for the magnitude of V. And what's the other variable we need to fill in for? Theta, yep. And in this case, what is theta? 30 degrees. Yep. So the first part of your formula is 50 cosine 30. And put the I next to it. So we know that that's the I component. And what's going to be the formula for the J component? Yeah.
50 sine 30.
50 sine 30 J. Now, 30 degrees is a multiple of 30. So I want to make sure when we do that, we write an exact answer. What is the cosine of 30 degrees from the unit circle? No, what's the cosine of 30 degrees? So that's going to give you a decimal. So we need some square roots in this. Sure. Anybody help him out? What's the exact answer for cosine of 30? It's a unit circle. We should definitely know that. Yeah.
It's pi over 6, I believe.
So that's an angle. That's 30 degrees in radians.
Yeah.
But that's not the cosine of 30 degrees. Yep.
It's either 1/2 or square root of 3 over 2.
Yes.
One of them is.
Yes. Yep.
Oh, no, it's y, so square root of 3 over 2.
It's the y value of the coordinate. Well, no, cosine is the x value of the coordinate, which is root 3 over 2. So remember, the coordinate for 30 degrees is root 3 over 2, 1/2, and you're looking for the x value. Now, the next one, we want the y value. That is 1/2. Okay, when we multiply that out as an exact answer, we get 25 root 3 I plus 25 J. That's the exact answer for the velocity vector. If they ask us to round to whatever number of decimal places, we can do that as well. Actually, I already typed it in. 43.30. All right, so we've written it as a velocity vector, but the last thing they said was to explain the meaning of each component. So what is that 43.3? Like I'm talking about if you did this as like a real world thing, you had an object projected at a 30-degree angle at 50 miles per hour, what would the 43.3 actually be? Yeah?
I guess like how far it goes, like horizontal.
Well, it is something horizontal, but remember, this is representing a velocity vector. It's not necessarily a distance of how far it traveled. Yeah?
Horizontal component.
Can you be more specific? Horizontal component of what?
Horizontal component of the velocity vector.
Yes, it's the horizontal component of the velocity vector. Could we say that a little simpler? I'm thinking we could say it in like 2 words. It's the Yep.
Horizontal speed.
Yeah, it's the horizontal speed. So that means if you were in front of this object and it was coming at you, it would hit you at 43.3 miles per hour if you just stood there and let it hit you. What about the 25? What's that?
The
the vertical speed. Okay, so how would that work? Well, if you were projecting this object and you put your hand right at the end of the, say like a cannon or something that was projecting it, and the second it left the cannon, it hit your hand. It would hit your hand and come up at your hand at 25 miles per hour. Right? If you put your hand in front of the cannon, it would hit it at 43 miles an hour. So that's the speed of the object the second that it leaves whatever projected it. This number is constantly changing because the second that it leaves whatever projected it, the vertical speed is going to slow down. So it's going to go up, it's going to go up, and go up, and eventually the vertical speed is 0. Then it comes back down. If you don't include air resistance, then the horizontal speed never changes. That is the same the entire time. The only thing that slows that down is the thickness of the fluid it's traveling through. In this case, air or whatever. And that fluid can make a big difference. Like if it's underwater, well, that's going to slow down very, very fast because it's a thick fluid. But we're pretending like we're in outer space, so that number doesn't change. And technically, that number wouldn't change if you had no gravity. Okay. So any question on the velocity vector? Yeah.
On the question on the test, would you ask for the decimal point or the 25 root 3?
It could be either one. So I would say anytime you're working with trig functions that are multiples of 30 or 45, I could always ask for an exact answer to that because that's on the unit circle. Yeah. Probably wouldn't ask for an exact answer of like a 15 though. We did do the 15s, but then you got to do the sum and difference identities, so that's a little bit more involved. The only time I would ask for that is if that was the specific question I wanted to know. But not in something like that. Okay, anything else on that one? All right, so last problem. Okay, the last problem is going to be about forces. So the problem we're going to look at, it's called static equilibrium. Okay, static means that something is not moving. Static, think of like stationary. And equilibrium means balanced. So what's happening in this problem is the object is not going to be moving because all the forces acting on it are balanced. Now we're going to be dealing with 2D. Okay, we're not going to deal with 3D. So in 2D, how many different axes do you have? Yep, two. Okay. What are the directions of the two axes?
Like up, down, left, and right.
Up and down, and left and right. If an object is not moving to the left, then what does that tell you about the force, another force? If it's not moving left, then it must be because of something. What would it be because of? Yeah?
Is the equal force in the opposite direction?
Yeah, there's something balancing it in the opposite direction. So if it's not moving to the left, that's because the force to the right is equal to it. Right? Now, if the object is not moving down, that's the other direction in 2D, that would be because of something. Yeah?
What's going to be opposite direction? What would be up in this case?
Right. So if the object is not moving down, it's because there's another force that must be counteracting it in the opposite direction, which is up. Right? That's why this object here doesn't move. It's not because it doesn't have any weight. It has weight. It's heavy. It weighs something. But it's not going down because the floor is pushing up. All right? So what we want to do is look at a problem, and we're basically going to find the tension in two cables supporting an object. Now, first thing to understand is the tension in the cables can be more than the object weighs. How can that happen? Well, imagine you had a rope that weighed like 20 pounds, and you use it to do a tug of war. If there's 20 people on one side of the rope, like 20 people on the other, does that mean the rope can only have as much tension as it weighs? No. You can get a lot more tension in that rope when you start getting that many people pulling on it. So tension is related to how heavy the object is, but it's also related to the angles that it's being supported at. If all the supports were vertical, okay, like on the lights, if all the supports were vertical and they're all equally spaced, then yes, the total weight supported by each cable is the weight of the lights divided by the number of cables. It's all equal. But when you start putting cables on angles, that doesn't work. It gets more complex. So we're going to find the tension. I'm going to call this tension in cable 1. We'll call that tension in cable 2. All right. This object is not moving. So can somebody tell me again, we're going to write two equations. What does that mean? If this object is not moving, it means that something equals something.
The force pulling down and the force pulling up are equal to 0.
Yeah, so the force, I'm going to write it like this. So the force up is equal to what?
Equal to the force down.
Is equal to the force down. Okay, this is going to be very conceptual. There's going to be no numbers in this yet. Force up equals force down. And what else is happening? If it's not moving. Yeah.
The force left equals the force right.
So force left equals force right. That's the basis for the whole problem. What we have to do now is start translating that into our diagram. Okay, I'm just going to move this down a little bit. Okay, I need to figure out some labels for all the forces. What I need to do is break each cable up into its components. We need to start thinking of it as left and right and up and down, not at an angle. What direction is, we'll call it cable 1, the right side. What direction is that cable pulling in? Yeah?
Right.
Okay, right and up. Because if you were to cut cable 1, the object would swing down and to the left. So it's not swinging down and to the left, so there must be something pulling it up and to the right. So it's pulling this way. What direction is cable 2 pulling in? Yep.
Up and to the left.
Up and to the left. How am I going to visually show the components of those two cables? What am I going to draw to do that? Yeah. Yeah. What kind of triangles?
Right.
Yeah, we're going to make right triangles. So what we need is a line right there. We're going to make, just put, close enough. We'll put one over there. Okay, so I just drew some parallel, vertical, and horizontals to make some right triangles. That's 90. That's 90. Cable 1 is pulling to the right, and it's also pulling up. The red and the blue vectors represent the horizontal and vertical components of cable 1. Okay, same thing's happening in cable 2. It's pulling to the left and up. All right. When we're describing a horizontal, we should stick with the letter X. And when we're describing a vertical, we should use the letter Y. It's just easier to remember that way. So I would call this X1. That's the horizontal component of cable 1. What would be a good name for the blue arrow on the right side? Yep. Y1. Yep. That's the vertical component of cable 1. What would be a good name for the red component pointing to the left? Yep. It's another horizontal component, but it's part of cable 2. And the blue arrow, yep, Y2. So now let's substitute all those names in, along with 1,200 pounds, into our equations. Okay, force up. What's the force up in this picture? Yep. Can you be more specific?
Either Y1 or Y2.
Y1 and Y2. They're both up. Yep. And they're working together. So Y1 plus Y2. That is the amount of force up. What is the force down in this case? Yeah. That's what's trying to fall to the floor, 1,200 pounds. Okay, so we got that. Now, what's the force left? Yep. X2. And that's balanced by the force to the right, which is? Yep. X1. Okay, so that's a little bit better. We're getting a little further away from being conceptual and a little bit more concrete relating to our problem. But these formulas are not taking into account any of these angles. So now we got to take into account the angles. What I would do is find each of these angles in the bottom of the triangle. How much is this angle in the lower left? Yep. 45. There's lots of ways you can figure it out. But you have two parallel lines, and you have an intersecting line, so the alternate interior angles are the same. So 45. And that means this one over here would be how much? Yep. 30. Okay. Let's start with the triangle on the right. I want to use this angle, this side, and that side. And I want to relate all three of those with a trig function. What trig function would connect those three quantities? Yeah.
Cosine?
Cosine. And can you tell me what you would fill in for that?
Cosine of 45 equals x1 over t1.
X1 over T1, yep. And if you solve it for X1, what do you get? Yeah.
T1 cosine 45 degrees.
T1 cosine 45. Follows exactly the same pattern as the velocity vector. Hypotenuse times your cosine gives you your horizontal. Okay. Based on that, anyone think they can tell me what y1 would be? Yep.
T1 sine 45.
T1 sine 45. Okay, so there's y1. Now we need x2. And we need y2. What is x2 gonna be? Yeah, Matt.
T2 cosine 30 degrees.
T2 cosine 30. And what about y2? Yeah,
T2 sine of 30 degrees.
T2 sine 30. Okay, now, the physics part is done, right? That was just making this kind of concept. Up equals down, left equals right. The trig part is done. Converting all your horizontal and vertical components into trig equations. Now we've got to substitute all those in, and then we're going to have a system of equations we need to solve. Okay, so we've got y1 plus y2, so that's t1 sine 45 plus t2 sine 30 and that's equal to 1200. So here's your first equation. And the second equation, x2 equals x1. T2 cosine 30 equals x2 equals x1, t1 cosine 45. Okay. We have two different variables. We have two different equations. That's a standard two-variable system of equations. What's one method you can use to solve a system of equations? Yeah. Substitution. And that's what I would do here. Which equation do you think is easier to get a variable by itself, the top or the bottom? The bottom, yeah. Doesn't matter which one. Let's do T2. T2 is T1 cosine 45 divided by cosine 30. Okay. So now we have a formula for T2. What are we going to do with that? Yeah.
Plug into the T2 in the top equation.
Yep. We're going to plug it in for T2 in the top equation. So now we've got T1 sine 45 plus, we're going to fill in T2. So it's T1 cosine 45. That's going to take the place of everything I just circled. T1 cosine 45 over cosine 30. And don't forget the times 30 that's next to it. Sine 30. All right, now I need to do that out. Okay, sine of 45 is 0.707. Plus, I don't know what all that is. So I'm going to do cosine 45 times sine 30 divided by cosine 30. Okay, that is 0.408 T1. Okay, so I multiplied all of that together and divided. What would I do next on the left-hand side? Yeah, what would I do next on the left-hand side? Yeah. Combine my terms. Okay, so we've got 0.707 and 0.408. 1.115? 1.115. And my last step to get T1 alone would be divide by 1.115. So 1200 divided by 1.115. 1076.23. that is the tension in cable 1. Once you know the tension in cable 1, well, tension in cable 2 is easy. Just fill in the number you just got for tension in cable 1 and do that up. Okay, so that's a static equilibrium problem, and there's one just like that in the homework. It's exactly the same steps, just different amount of weight and I think different angles for the cables. Okay, so let me put up the homework. There are 2 questions I need to change. Let's see. It's definitely this one. I think it's 64. Yep, 64. Okay, so that's the homework for tonight. 25 to 47, those are odds. 55 and 57 are velocity vector problems, and 66 is a static equilibrium. Yeah. Take a picture of it? Sure.
Probably.